Welcome to Unit 7, Chemical Quantities. And this is a super fun unit because we are continuing our nuts and bolts chemistry topics. In the last unit, we talked about different types of chemical reactions and balancing chemical reactions. And in this unit, we learn how scientists quantify different chemical amounts. And so if you've ever wondered, well, how much active ingredient is in the medicine that I take? Or if you're spreading fertilizer in your garden, how much nitrogen is actually in this bag of fertilizer? Or you might be wondering what the acceptable amount of a pollutant is in a local stream or coming out of smokestacks in a factory in your town. Well, these are some of the questions that a knowledge of chemical quantities can provide for you. And in this unit, we'll talk about the mole concept and about how to get a better hand around the ratios that are in chemical reactions or chemical compounds. And we will be able to take those ratios and convert them into mass amounts. So you'll actually get a quantity in grams of the chemical in a certain amount of a chemical compound. So this is a cool unit, and we start off by talking about the mole. Okay, a mole is not a furry critter that lives under the ground, although that is a mole, but a mole is our term that we use for a grouping of objects. A mole is not a little guy that lives under a bridge. That's a troll. A mole is a group of objects, like a dozen is equal to 12, or a pair is equal to 2. So you may be asking yourself, well, why do we use the word mole as a grouping? Well, I think it goes back to a Latin term. A mole means a bunch of stuff, basically, in Latin. And so it's a grouping of things. And in chemistry, a mole is equal to 6.02 times 10 to the 23rd objects, atoms, particles, formula units, just any quantity, just like a dozen is equal to anything that has 12 in it. So that is the number we use. And that's a really huge number. And we'll talk about the reason why here in a little bit, why that big number. A mole is sometimes referred to as Avogadro's number. This is in reference to an Italian scientist, Emilio Avogadro, and he was working on grouping things and doing chemical ratios, and it's a tribute to him and all the work that he did. And this number is so large because atoms are so small and numerous. And so if we just talked about atom ratios or particles or molecule ratios, these numbers that we would have to deal with would be huge. And so we group these in this mole bucket. Say 1 mole is equal to 6.02 times 10 to the 23rd objects. And that makes the numbers easier to deal with, these ratios easier to deal with, so we have smaller numbers to try to figure out. The number was chosen, that specific number was chosen because that's the number of atoms in exactly 12 grams of the carbon-12 isotope. So 12 grams of the carbon-12 isotope contains exactly 6.02 times 10 to the 23rd atoms. Of course, carbon makes up all of life forms, and so that particular substance was used because it's so vital in all that we do. So if you have 1 mole of carbon atoms, including all isotopes, it weighs 12.011 grams. We call this weight the molar mass. And you can find the molar mass on the periodic table. We've already talked about that when we talked about isotopes and how we calculate the molar mass from the weighted average of all the isotopes of the element. So if you look on the periodic table at carbon, Carbon is atomic number 6 on the periodic table. It has 6 protons and 6 electrons in a neutral atom. And if you combine the weighted average of all the isotopes of carbon, carbon 12, carbon 14, etc., it would weigh 1 mole, or 6.02 times 10 to the 23rd atoms of carbon would weigh exactly 12.011 grams. And so it would weigh a little bit more than carbon 12 because carbon has some heavier isotopes as well. But carbon 12 is the most dominant isotope because it's closest to the molar mass. So what does 1 mole of oxygen weigh, and how many atoms does it have? I'll let you think about that for a minute. Okay, so where would you find that? Well, you would find the weight on the periodic table, right? The non-whole number on the periodic table. It's usually underneath the symbol. And on my table, it actually rounds it to 16.00 grams. It's actually 15.998, something like that. The one I'm looking at now, the periodic table, says 16 grams. And how many atoms does it have? Well, 1 mole of anything has 6.02 times 10 to the 23rd. So it's just kind of like a dozen. If you had a dozen baseballs or a dozen basketballs, how many basketballs would you have? 12. How many baseballs would you have? 12. Would they weigh the same? No, they would not. The baseball and the basketball have different masses or weights. I usually give the example of bowling balls in baseballs. So if you had a dozen bowling balls, you'd have 12 bowling balls. If you had a dozen baseballs, well, you'd have 12 baseballs. But the bowling balls would weigh more than the baseballs. So the thing that's the same about a mole of anything is that they have the same number. The masses will be different for different elements on the table as well. Okay, so here we have 15.99 grams and 6.02 times 10 to the 23rd atoms. What does 6.02 times 10 to the 23rd atoms of phosphorus weigh? Okay, I'll let you think about that for a minute. You can look it up on the periodic table. It would weigh 30.973. You know, that's a big old long number. It must have a very precise scale to weigh something with that many decimals out, right? How many moles are in that? Well, 1 mole weighs that amount. We find that on the periodic table. I don't seem to be beating you over the head with this, but it's really important that you understand the concept and the general concepts behind this. How many moles are in 28.80855 grams of silicon? 1 mole, which has 6.02 times 10 to the 23rd atoms of silicon. The atoms for 1 mole will always be the same. The weights will change. Moles to atoms conversions. Okay, so I'll give you a minute to write this little flow chart down, and then we'll talk about it in more detail. So atoms to moles, or moles to atoms, we use Avogadro's number to convert back and forth. But moles to grams and grams to moles, we use the molar mass. And we'll work some problems with these. I always think it's nice to jot down this little flow chart until you get familiar with the conversion so you won't lose your way, and maybe use Avogadro's number when you should have used the molar mass, or the molar mass when you should have used Avogadro's number. Okay, so this first problem says how many moles are there in 1.806 times 10 to the 24th atoms of nitrogen. And so I'm going to use a method called the factor label method that we used to make our metric conversions earlier in the group of lessons when we did metric to metric conversions. And this will serve you well in all these different types of chemical conversions. And so let's pick up our pen here. And the very first thing that we're going to do is we're going to underline what we're solving for. So we're solving for moles. So we're solving for this guy right here. And we are given 1.806 times 10 to the 24th atoms. So let's write that down. So we're writing down our given. So we're given that many atoms of nitrogen. And then we're going to convert. So we're going to use our conversion factor. So like before, whatever unit that we're starting with, atoms of nitrogen will go on the bottom, and whatever we're solving for will go on top, which is 1 mole. Okay, so whenever we're going from moles to atoms, or atoms to moles right here, we use Avogadro's number. So it's 6.02 times 10 to the 23rd atoms. So the unit of atoms will cancel out and our final answer will be in moles. So let's take our calculator out and do that. I'm going to pause the video for a minute because I didn't have my calculator with me. Shame on me. And then we will do the calculation. Okay, and I get 3. So very good, right? So it's going to be 3.000, right? Of course, this is times 10 to the 24th. I neglected to put that down. Got a little excited about doing our first molar calculation. So there's 3 moles of nitrogen in that many atoms of nitrogen. Let's see if we have another problem to work. How exciting. Okay, so the next one says, how many atoms of chlorine are in 2.5 moles? All right, of chlorine. So we've got 2.5 moles of chlorine. We're solving for atoms. So this time, moles will go on the bottom and atoms will go on the top. Okay, so moles to atoms, atoms to moles. Always we will use Avogadro's number. We'll always put a 1 in front of the mole amount, and then 6.02 times 10 to the 23rd will go next to our atoms amount. Moles will cancel, moles of chlorine. And then we will be left with atoms of chlorine. Let's do that one. We only have 2 significant figures here, so we'll just put 1.5 atoms of chlorine. Okay, very good. Easy cheesy, right? Moles to atoms, atoms to moles. Okay, got another one. How many moles of radon are in 2.709 times 10 to the 24th? So we're starting with atoms this time. Atoms of radon. Radon is an interesting chemical. It is a noble gas and it is a radioactive material, and it is an alpha emitter. And in Kentucky, since we have a karst environment, one where we have a lot of caves, the breakdown of the minerals and rocks produce a lot of radon gas. And radon gas, if you breathe it over a long period of time, can cause you to have lung cancer. And so it's really super important in our area to get your home checked for radon gas. And if your home has it, there are ways to mitigate that or to pipe it away from your structure. Notice here, whatever's on top always goes on the bottom. So atoms here go on the bottom, and then we do our division. So it's 2.709. We get 4.5 moles of radon. Or in. Okay, there we go. It's important to put the unit and the chemical on all these so people, when they look at your number, will know what you're talking about. Mole to mass conversions. Okay, So now we are going to be dealing with the molar mass off the periodic table. So we'll be working on this part of our flow chart. It says how many grams are in 2.5 moles of chlorine. Okay, so we underline grams here. Be 2.5 moles of chlorine. You'll be tempted just to write 2.5. And I'll caution you against doing that because 2.5 what? So it's easy to get lost, and then we will be doing some more complicated conversions later where you're going to for sure want to label everything really well, and please do so now. It will treat you well as you go along if you always put the unit and the element symbol or chemical there. So we have moles, so moles will go on the bottom of our conversion factor, moles of chlorine. We are solving for grams of the same. And now it'll be 1 mole. But to find the amount of grams, we will look at the molar mass. How many grams are in 1 mole of chlorine? So we look on the periodic table, it's 35.45. We'll round it up to 35.5. Whoever your teacher is, ask them how they want you to round it. If you need to use all the numbers on the periodic table, round to the hundredths place or the tenths place. We'll round to the tenths place just to make it easier. 7.5, and we'll just say 89 grams. Okay, so we're going to say that this is an exact conversion here. Our conversion factor, we have 2 significant figures here, so we'll have 2 in our answer. Grams of what? Grams of chlorine. Okay, very good. All right, and so now it says how many moles are in 268.7 grams of neon. So this time we are given the gram amount, and we're going to go to the mole amount. Okay, so we're given 268.7 grams of neon. Neon lights, right? The bright lights of Broadway are neon. You can do all sorts of cool things to color that gas and make cool neon lights. Those are really come back now and are really popular. And so now we start with grams here. So the grams will go on the bottom of our conversion factor per 1 mole. So 1 mole of neon, grams per mole of neon, let me look that up, 20.18 on the periodic table that I got. So we'll say 20.2. And now we just divide, we multiply across the top, 268.7 times 1, divided by 20. Okay, following along, we got 1, 2, 3, 4 significant figures, so we'll have 4 in our answer. So it's 13.30. So that'd be 4 significant figures. Grams of neon. Very good. Very good, very good. Fun. Do we have another one? Yes, we do. How many grams are in 1 mole of boron? All right. So this one is really simple. We just have to look on the periodic table, right? I hope I'm not boroning you. Okay. So boron, 10.81 grams. Look that up on the periodic table. 10.81 grams. With a smiley face because we just had to look it up. Mole to mass using molar masses of compounds. Okay. So first we're going to just do molar masses, and this is fun, and a essential skill. So what if it was not just an individual element that we are dealing with, but a whole chemical compound, in this case an ionic compound of sodium sulfate. So let's do that. We have sodium, we have sulfur, and oxygen in our compound. And a chemical compound is not only a ratio of atoms, but it's a ratio of moles as well. So if we had this chemical compound, we would have 2 atoms of sodium, 1 atom of sulfur, and 4 atoms of oxygen. And then if you had a mole of that, you would have 2 times 6.02 times 10 to the 23rd atoms of sodium, or 2 moles of sodium, 1 mole of sulfur, which would be 6.02 times 10 to the 23rd atoms, and then 4 moles of oxygen, which would be 4 times 6.02 times 10 to the 23rd atoms of oxygen. And so that if we did atoms, it would be a huge number of atoms. And so we regroup them in these mole buckets to make it a lot easier. And so we have 2 moles of sulfur, 2 moles of sodium, 1 mole of sulfur, and 4 moles of oxygen. When I do my molar masses, I put my moles in parentheses, and then I look up the mass of 1 mole of each one of the elements. And sodium is 23, I think, 22.99. So we'll round that to 23.0 grams. Sulfur is 32.1. And we'll round oxygen to 16. And so now what we do is we multiply the mole amount by the molar masses. And let's see what we get there. 2 times 23, I think I can do that, is 46 grams per mole. 32 grams per mole. 4 times 16 is 64 grams per mole. Well, in this case, grams total. The grams per mole is 23, 32, and 16. And so then you add those up. So it'd be 142 grams per mole of Na2SO4. Or the molar mass would be 142.0 grams. I'm double checking my math there. All right, I think we're good. So what is the molar mass of aluminum phosphate? Okay, I think I did this one because the calculating the number of moles is maybe just a little bit tricky. Let's see here. We'll do it right here. We've got 2 moles of aluminum. Phosphorus, it's 3 times 1 would be 3. What's ever on the outside of the parentheses, you multiply by what's in. And oxygen would be 3 times 4 is 12. There. So we have our mole amounts. Now we need to look up the molar masses on the periodic table. Al2PO3. There we go. Fun, right? All right. So now we are going to do a grams to moles problem using the molar mass. And I am going to erase a little bit here. Hopefully you got this written down. If not, pause the video and write it down. This is a 12 here. Let's make that one of the compounds above to make it a little bit easier since we have the molar masses already calculated. So instead of kill, we are going to cross this out. Okay. 3.5 moles of Al2. That will be a way cool problem. Okay. So we're going to final answer will be in grams of Al2PO43, or aluminum phosphate, right? And we'll start off with 3.5 moles of that. Notice here how I'm modeling great behavior by labeling everything. I just don't write moles. I write moles of what we're calculating, right? So for every 1 mole of that, since we have moles on top, it goes on the bottom of our conversion factor. We got so many grams of the same. Okay. And we've already calculated the grams per 1 mole of Al2O3 by going through and looking at the molar ratios and the molar masses and adding all those up. So we've got 339 grams per mole. So it's 3.5 Moles will cancel, right? And so it's 3.5 times 339 divided by 1. And I get 1,186. And you notice here we got two significant figures. So here we could say we have 1,200 and leave out the decimal place, right? The actual number is 1186.5. Since we're rounding to two significant figures, we'd say 1,200 grams. Just like that. Okay. Cool, cool. And then we got another problem on the bottom. This is how many moles. So I'm going to erase this so that we can see our work. Hopefully you've got that written down. If not, just go back and pause the video and write it down. Of Al2PO4 3 grams per 1 mole of that substance is 339, right? So in this one, it's 360.7 times 1 divided by 339.06. And we have 1, 2, 3, 4 significant figures, so we should have 4 in our answer. Moles of Al2PO4 3. Very good. Our flow chart here again. How many atoms of chlorine are in 100 grams of chlorine? Okay, so here we've got grams, and we're going all the way over here to atoms. So we're given grams and we're going to atoms. So we're going to have 1, 2 conversions. So a 2 conversion problem. So 100 grams of chlorine. So I don't forget a step, I'm going to make both my conversion factors. Grams of chlorine will go on the bottom per 1 mole. And I think we said that that's 35.5. And then for every 1 mole of chlorine, we've got 6.02 times 10 to the 23rd. See here, then grams of chlorine will cancel out, moles of chlorine will cancel, and we'll end up with atoms of chlorine. So grams, here, grams to moles, and then moles to atoms, So it's 100. This is 100.0, by the way. So we got 1, 2, 3, 4 significant figures. 1.696 rounds 695 something atoms of chlorine. How many formula units are in 45 grams of NaCl? Okay, so formula units. A formula unit is this whole big thing together. Okay, so in this case, you have 1 atom of sodium and 1 atom of chlorine in the formula unit. So we treat that like one big thing. So in our example of dozens, if you have a nut and bolt, let's say you have a nut and 2 bolts, and that makes a set. Well, how many nut and bolt sets would you have in 12? Well, you would have 12. Or I'm sorry, how many nut and bolt sets would you have in a dozen? Well, you would have 12 of those. But you would have 12 times 3 parts, right? The nut and the 2 bolts. In this example, we're doing the whole unit together, the formula unit together. And so we have 45.0 grams of sodium chloride. So we'd have grams of NaCl here per 1 mole. And then from every 1 mole of sodium chloride, we'd have 6.02 times 10 to the 23rd formula units, those whole units together. So now we got to get a molar mass for sodium chloride. We'll do that up. Let's do that over here. We've got sodium is 23 grams and chlorine is 35.5. So you got 5, 8, and 5, 58.5 grams. Okay, so it's 45 times 6.02 times 10 to the 23rd formula units. Sodium chloride. Okay, very good. How many molecules are in 100 grams of water? Okay, so formula units are for ionic compounds. Molecules are for covalent compounds. So we have 100 grams of high quality H2O, as the water boy would say. Grams of H2O per 1 mole of the same. And for every 1 mole of H2O, we have 6.02 times 10 to the 23rd molecules of water. Okay, so water's weight is 2 times 1 would give us 2, and oxygen has a molar mass of 16. So you have 18 grams per mole there. Okay, so 18 would go on the bottom. And let's work that one out as well. 3.34 times 10 to the 24th molecules of water. Very good. All right. So these are multiple steps. They are a little bit more difficult. But the main thing to do is to find what you've got. Like if you have atoms and you're going to grams, or if you have moles and you're going to grams, you'd have one step. If you have atoms to moles, it's one step using Avogadro's number. But if you're going from atoms to moles, it will be 2 steps, or atoms or formula units to grams, or molecules to grams. It will be 2 steps. Okay, so now we have a little bit of a wrinkle to mass to atoms type of problems. And in this particular problem, we are going to calculate the atoms of phosphorus, just phosphorus, and aluminum phosphate. And so we are interested just in the phosphorus part of the compound. And you might ask yourself, well, how do we do that? Well, we get to moles of the compound, Al2PO43, aluminum phosphate. For every so many moles, we have 3 moles of phosphorus. And then we can get to atoms of phosphorus, multiplying that by Avogadro's number. And so let's do that. Let's underline what we're solving for first, atoms of phosphorus. So that should be our final answer. We're given 50.5 grams of the compound aluminum phosphate, and we're going to convert that to moles. So for every many grams of aluminum phosphate, we have 1 mole of that critter, aluminum phosphate. So for every 1 mole of aluminum phosphate, we have 3 moles of phosphorus. And then finally, for every 1 mole of phosphorus, we have 6.02 times 10 to the 23rd atoms of phosphorus. All right. So now all we need to do is write down or calculate the molar mass of aluminum phosphate. And so I think from previous slides, we knew that that was 339 grams. Okay. So now what we do is we multiply across the top and divide by the bottom. So do that. When you do that on your calculator, be sure to put parentheses around the top fraction and the bottom fraction so you don't get the order of operations messed up and maybe get a wrong answer. Okay, so we get 2.69 times 10 to the 23rd. Okay, very good. So that's a little bit of a wrinkle. Notice here that you can use the chemical equation as a conversion factor when you're going from trying to figure out parts of the chemical equation. The next one's a little a little bit more tricky. Let's talk about it for a second. It says, how many atoms are in 35 grams of Na2SO4? Well, you have 2 moles of sodium, 1 mole of sulfur, and 4 moles of oxygen. So you would have 2 times 6.02 times 10 to the 23rd atoms to get your atoms of sodium, and 1 times 6.02 times 10 to the 23rd for sulfur and so forth. But you don't have a whole mole amount because you only have 35 grams. So you have to convert the grams to moles of the compound, and then moles of the compound to atoms of the compound. So let's do that. So we'll underline atoms. So atoms of the whole thing. And we got 35 grams. So we've got grams here per 1 mole of the compound. And unfortunately, I don't know that, but we'll get that here in a minute. And so for every 1 mole of Na2SO4, we have moles of the compound, I guess you would say. Okay, so we have 2 moles of sodium, 1 mole of sulfur, and 4 moles of oxygen. So 4 and 2 make 6, and 1 makes 7. So we have 7 moles total in the compound. And then for every 1 mole of anything, you've got 6.02 times 10 to the 23rd atoms. So that's how you would calculate that out. Let's do the molar mass for sodium sulfate. Sodium, there's just 1 mole of that, 23. Okay, so now we'll multiply across the top, 35 times 7 times 6.02, and then we will divide that by 142. 35 times, so here we have 1.038. 3 significant figures, that would be 1.04. I'm going to write down here 1.04 times 10 to the 24th atoms in 35 grams of Na2SO4. Sometimes it's kind of nice to circle answers. Alright, so that kind of concludes recording 1. We covered a lot of ground. There are a lot of practice problems for you to do in the practice set. We will be doing recording 2 and putting that up for you here. And in recording 2, we'll be talking about some other problems that need this skill set that we've just covered to work on. We'll do percent composition and empirical and molecular formulas, and then we will talk about concentrations of solutions as well. So this ends chapter 7 or unit 7, recording 1, and looking forward to seeing you to do some more chemical math in recording 2.